Hi, Algebra 2. Just wanted to go ahead and put together a real quick notes video on some of the things that we had talked about today in class regarding solving systems of linear equations using algebraic methods, so substitution and elimination. So the last class meeting that we had, we talked a little bit about solving systems graphically. And recall a system of linear equations. Right now we're talking about two equations with two variables. Can have more equations, can have more variables, but right now we're talking about two equations, two variables. And we talked about graphing each equation and then using that to go ahead and solve the system, because we could identify the point where the two lines intersect. That point would be on both lines. Any point that's on a line makes that a true statement. So if the point is on both lines, that means it solves both equations. And that's our definition for solving a system of linear equations. But one of the things that we found is if you're kind of haphazard with your graphing, we look at this graph here, and it looks like it might kind of be close to 1, 1, but it's actually not. If you follow the grid lines, where this intersection point is actually inside of this grid square. So that's maybe about 0.8 or 0.75 for the x and 1.2 or 1.25 for the y. We can't really be sure. Now, miracles of modern technology, I love it here in the 21st century. If we go and we graph both of these in Desmos and then click on that point of intersection, it's going to tell us exactly what that coordinates of the solution are. But if we're working without technology, sometimes finding the solution from a graph is not always that easy. So we're going to look at two options that you have, two methods for solving systems algebraically. One is called substitution, the other called elimination. So go ahead and pause the video, and you can write down this definition for substitution. So in substitution, you solve one equation for one variable, and then substitute that expression into the other equation. So it works well when one or both equations are already solved for a variable or can easily be solved for a variable. So let's look at an example. So here we can see that we have one equation that's solved for a variable, y equals x plus 2. So this one is an ideal candidate for substitution. Let's think a little bit about what we know about the equal sign. Recall it back in grade school that really just told us, hey, here's where the answer goes. But now that we've moved on to some more advanced math, the equal sign is making a statement. This expression on the left side and this expression on the right side have the exact same value, even if they look different. It's like 4 quarters and $1. Like you can trade out the 4 quarters for $1. They look different, but they have the same value. And it might help you solve a problem. Like if the vending machine won't take your solid dollar, but if you trade with a friend for 4 quarters, it'll take your quarters. So these two have the same value. The other thing we know is we're dealing with a system of equations. So these two y's are going to have the same value. So this is equal to this, and this is equal to this. What that tells me is this expression, x plus 2, I can substitute it into this other equation in place of the y. So instead of x plus y equals 8, I've got x plus 2 equals 8. So combining like terms, 2x plus 2 equals 8. Subtract 2 on both sides, and divide by 2, and x equals 3. Now step carefully here, because we've so accustomed ourselves to, hey, I've got a variable equals a number, I'm done solving, yay. When we have a system of linear equations, if it's two variables, two equations, our solution is going to be an ordered pair. So I know the solution happens when x equals 3, but what's my y value? So now I can substitute this 3 into either of these equations for x and solve for y. And I get a pick. So I'm going to take the one that's easiest to work with. This equation is already solved for y, so it's just plug and chug with the x. So y equals 5. Okay. And remember, you can always know for sure if you're right, because you take the x and the y, you substitute them into both equations, and it should make both of those true statements. So if y is 5 and x is 3, 5 equals 3 plus 2, yep, that checks. How about if x is 3 and y is 5? 3 plus 5 equals 8. Awesome, that's true also. Now you notice that this is a pair of integers for our x and our y. If we solve this by graphing, it wouldn't be super challenging, right? But it's not always that way. So I want to take a look at another example. So in this example, neither of these equations is solved for y right now. And we see that both are pretty easy to solve for y. I could subtract 2x from both sides here, or add 8x on both sides here, and that's what I'm going to do. So y equals 8x plus 1. These two expressions are equal. My other equation is 2x plus y equals 6. So I can take this 8x plus 1 and substitute it in place of this equation in place of the y. Equals 6. So go ahead and pause the video, and you can solve this equation on your own. Check your work against mine. So let's take a look at how that would go. So 10x plus 1 equals 6. When we subtract 1 from each side, 10x equals 5. And so x equals 5/10 or 1/2. So again, reminding ourselves that our solution is going to be an ordered pair. I just substitute my x in to one of my original equations. And we find out that y equals 5. So in this case, if I did graph this, my solution would end up inside of one of the boxes of the grid marks. Much more difficult to know for sure that it was 1/2. All right, so one of the things that we'll find out is solving for y is not always easy. As you saw in class in the notes on quizzes, sometimes when we solve for y, we get a really ugly equation that we would never want to work with. And many times in substitution, we end up using the distributive property, which you all know how to use, but sometimes you don't like to use very much. So we have another option, and that option is known as elimination. So pause the video and you can write down this definition. In elimination, you get rid of one of the variables by adding or subtracting the equations. And you may have to multiply one or both equations by a scale number in order to create variable terms that are opposite coefficients that can be eliminated. So let's look at an example. So here, neither one of these is going to solve very easily for y. But I do notice that I have a positive 3y and a negative 3y. When I add these two equations together, positive 3 and negative 3, those are opposites. They make a zero pair. So negative 3y plus 3y equals 0y. 0 times anything is 0, so that's just going to go away. 2x plus 4x is 6x, and then 34 and negative 4, 30. So 6x equals 30. And then following through, x equals 5. All right, so let's substitute our 5 back in. And we find out that y equals 8. So our solution here is 5, 8. All right, I'd also like to go in and take a real quick look at a couple of the examples that we had when we did our quizzes today. shrink my inset down a little bit. So let's look at one where we're going to use the distributive property with substitution. Y equals negative 3x plus 5, 5x minus 4y equals negative 3. So here I can see that I have an equation equal to a variable. We've solved for y. So let's substitute that into y here. So 5x minus 4 times negative 3x plus 5 equals negative 3. So distributive property, negative 4 times negative 3 is positive 12x. Negative 4 times 5 is negative 20. So 17x equals 17, and we're going to find that x equals 1. All right, and then substituting 1 back into our original equation. We find that y equals 2. So this is one case we may see where we have the setup to use substitution, but we also have to use the distributive property. Let's look at another example, this time using elimination. And so we had mentioned that occasionally when we do elimination, we end up in a situation where we have not opposite coefficients on the same variable. And we have to go ahead and multiply through one or both equations in order to be able to add them together. So here, I can't just randomly add these two together. If I do that, I'll end up with negative 2x minus 7y equals 21, which is a perfectly fine equation. It's just not any closer to being able to solve. I still have two variables. So if I want to add these two together, I need opposite coefficients. And the 5 and the 3 are a little bit messy, but here I can see negative 8 is a multiple of 1. If I multiply the first equation by 8, negative 40x plus 8y equals negative 24. The second equation is good as it stands. Now I can add these two together. Negative 37x plus 0y, and then, oh surprise, these two sum to 0 also, which looks a little strange, but we can still move forward with this. Negative 37x equals 0. Let's isolate the x by dividing both sides by negative 37, and x equals 0. So now we can substitute back into either one of our original equations, and I'm just going to use this one because it's in the window. So 3 times 0 minus 8y equals 24. So negative 8y equals 24 because anything times 0 is 0. Divide by negative 8. So now you've got some examples of a couple of different methods of substitution and a couple different looks at using elimination to be able to solve systems of linear equations. And keep in mind that you can use your notes on the quizzes. So I'm hopeful that you'll keep these handy and take a look at them. There's also a homework game that's set up on this quizzes. So if you wanted to go back in and practice these some more,